Good afternoon, everyone, and welcome to the ABC webinar, Biogas Membranes, Upgrading Essentials. My name is Caroline Pete, and I will be facilitating this webinar. Before we begin, I want to give a big thank you to Air Products for sponsoring today's webinar and making it free for all of you. Their sponsorship also directly helps the ABC and our programs. Before we get started with our content, I just want to make sure that you all know how to use our platform here. First of all, you should be able to see the slide that says quick notes, and you should be able to hear me. If your audio is bad, please check the audio pod in that GoToWebinar toolbar on the right side of your screen. You can also ask questions at any time throughout the webinar in that questions pod. You can also send us a message if you're having any issues, and we'll help you out there. And we're going to actually handle all the questions at the end of the webinar, but ask them throughout whenever they come to you. And as a reminder, we will be sending out the recording of the webinar and the slides this week in just a couple days as we get everything set up. So you will receive that. It's great to see so many ABC members registered today. Thank you for your continued support to make all that we do possible. For those of you who might not yet be a member, we're thrilled to have you with us as well. In case you're not familiar with the American Biogas Council, we are the voice of the U.S. biogas industry. We now represent over 370 organizations, which reflects the entire American biogas industry. And if you're not a member and you'd like to engage with us to help grow the industry and your business, please join the ABC through our website, americanbiogascouncil.org. So thank you, everyone, for joining us. I'm going to take this time to hand things over to our moderator, Paul Green with Green Tech. And Paul's going to kick things off and lead us through our great presentation we have today. Paul, it's all yours.
Thanks, Caroline. I appreciate it. Welcome, everyone. We're excited to have Air Products here teaching us about membranes for gas upgrading. So my name is Paul Green. I run a biogas RNG advisory service called Green Tech. So I was the first elected chairman of the ABC. So these projects are near and dear to me. So this continuing education is a wonderful feature of the organization. So it is a great time to be in the biogas RNG business, whether it's landfill gas, food waste, ag projects. Our customers, the off-takers, their thirst for buying RNG from us seems to be almost endless. So great to have highly capable suppliers like Air Products here with us to tell us about what they do. So with that, I'm going to hand the keys off to Rory Valletta. So Rory's the Global Biogas Product Manager for Air Products. So Rory, the floor is yours. And so we'll, again, hold questions until the end. And so you can ask them anytime, but we'll address them after Rory's done. So here you go, Rory.
Thank you, Paul, for the kind introduction, and welcome all today. And thank you for attending and showing interest in learning on membrane upgrading. Paul did a kind introduction, so I'll skip that. But I'm part of the group that's a little bit less known inside Air Products, called the Membrane Solutions Group, where everybody knows Air Products from the hydrogen projects in the US. Air Products has a long-standing history with membranes produced from out of St. Louis. Next, Caroline. Great. So today's agenda will be, I'm going to take you a bit more into membrane basics. A most common heard question is, what is a membrane actually? You see the vessel, but nobody actually knows what's inside or have seen what's inside, how it works. We're going to take a bit more closer look at system designs and configurations, as well as membrane and other technologies. I'm going to take you a bit more about some specific case histories where you might not even consider using membranes, but where you can use them. Next, Caroline. Great. As I said, the Membrane Solutions Group has been around since the 70s and from out of St. Louis, and we actually installed the first commercial installation in 1980. We produce enough fibers to go to the moon and back a couple of times a year. We're actually expanding the facility as we speak to even go to the moon more back and forth. We have experience in process gas applications where we separate syngas or steer syngas or do hydrogen recovery. We have experience in nitrogen systems in marine, oil and gas, as well as production facilities. We are the global leader in marine nitrogen generation for onboard inerting, as well as we have experience in aviation in the planes for nitrogen generation there. And the current focus for us is main focus is on biogas upgrading, where we partner with OEMs, so original equipment manufacturers who incorporate our membranes into their installations. We're a global partner where we can help you with a sales organization as well with a technical support organization. Next, please. While biogas is still upcoming in all the markets, also in the US, we've been active in the biogas upgrading and R&D project since 1994. Actually, even before that, some real pioneers in 1983 did some membrane testing on landfill gas upgrading. While the real increase in production and also in biogas upgrading started in 2012, we currently have over 175 references in the US, EU, and Asia, with a diverse feedstock knowledge, as well as landfill, manure, wastewater, biowaste, as well as the diverse utilization. So grid injection, CNG bottling, conversion to hydrogen, LNG production, and also one not mentioned here is CO2 liquefaction. Next, please. So what is a membrane? How does a membrane work? And what's selectivity and permeabilities? These are terms you probably heard when you came across a membrane manual. I'm going to explain a bit more on how it actually works. Next, please. So a gas separation membrane is a static, mechanical, chemical, and highly engineered separation mechanism. And I'm going to work backwards from the membrane you all see in your installations. That's on the left side. You can see the aluminum shell or stainless steel closed shell in different diameters and lengths. The picture to the right is a cutout of the membrane where you can see the polymeric fibers, which are bore side fat. Bore side fat means that the fiber internal is pressurized and gas is pushed against the tube sheet. That's the yellowish color you see. The tube sheet basically forces the gas into the fibers. If you get a closer look, there are a couple of thousand fibers per membrane. There are so many fibers inside the membrane so that you have a good area for separation. This is called the membrane fiber bundle, actually. Then the type of polymer eventually defines the final separation characteristics of the membrane. While the membrane looks as a closed vessel, it's a highly engineered component. Next, please. The main membrane characteristics are, the membrane separation is primarily intended to separate methane and CO2 from each other, where CO2 becomes the permeate, that's on the downside and the low pressure side, and this methane becomes a retentate or non-permeate. Methane is considered a slow gas, while CO2 is a faster permeating gas. With slow gas, it means that it permeates very slow through the fiber and wants to stay in the fiber. A fast gas permeates really quick through the fiber. Separation of nitrogen and methane is almost not possible with the current polymeric membranes on the market because they have the same characteristics. So they're both slow gases. CO2 and oxygen are intermediate, medium gases in terms of permeability, and therefore can be separated at a specific rate. The retentate stays on pressure, and the permeate will experience a small pressure drop versus the feed. Next, please. The main membrane characteristics are permeability, that's the amount of gas that can go through the membrane, as well as selectivity, how good the membrane is at separating the molecules, primarily being methane and CO2. To make it more visual and understandable, I always make the comparison to the door policy of a nightclub. So if you have a high permeable membrane, that means there's a big door where a lot of gas can go through in terms of flows or molecules. Low permeability means a small door, so you cannot push that much gas or people through the door. High selectivity means there's a door policy. People want to check your ID at the gate and then not everybody through. While low selectivity, they can basically let anybody through, or it's easy to get in. Next, please. These were membrane basic characteristics in a very high, quick level overview. However, there are many more variables that give a successful membrane RNG upgrading plant. And those variables that we need to take consider now are pretreatment, the membrane configurations, because we looked at membrane per membrane basis, but you need to configure them in a specific setup to achieve a certain performance. And we're going to look at operating variables. So how can I play with my plant to achieve a certain performance? Next, please. Pretreatment is key in the membrane performance. Everybody here knows that the raw biogas is not just methane and CO2. There are many, many byproducts. One of them is, of course, moisture, H2S, ammonia, oxygen, nitrogen, volatile organic components like VOCs, siloxanes, particles, oil, and many more that are there in certain amounts. However, these components require removal before the compressor. That's a piece of equipment you want to protect as well, and or the membrane feed. If both components, as well as compressor's membrane, would fail, then you basically experience unexpected downtime. So it's very important to remove these. Removal of these components can be done by activated carbon or chillers or other type of filter media to remove these. Next, please. Besides the membrane characteristics, the way how the membranes are lined up is essential for meeting a required performance. We call the way how membranes are lined up in a configuration where membranes are put in stages, a configuration where membranes are put in stages. A stage can consist out of multiple membranes. So that means if you talk about the first stage, it can be 4 or 5 membranes. A second stage can be also 4, 5, 6, or multiple membranes. The most simple configuration is a one-stage configuration you see in the left top picture. Basically, is a one membrane stage that consists of multiple membranes that separates the methane into CO2. Hereby is the CO2 purity relatively low, as well as the methane recovery is relatively low. More common configurations are on the right. So the 3-stage cascaded or 3rd, 4th stage cascaded on the complete right. The first stage is always the bulk separation. Hereby we separate the majority of the CO2 from the raw biogas stream. The second stage determines the methane purity. So what purity do you need? Grid injection. This stage defines it. The third stage defines the recovery actually. So of every molecule I feed into the gas or into the system, how many molecules can I recover? Any additional stages in series or cascaded or parallel basically increase methane recovery and our methane purity, but also they give process complexity. Next, please. Now we've discussed the membrane. So you're going to pick a specific membrane with a specific characteristic in separating, say, a membrane with a high permeability and a relatively high selectivity. You picked a configuration, let's say a 3-stage configuration, and now you have an existing plant. Besides that, these are parameters you can, design parameters you can pick up front. Now you're going to have two controllable parameters, temperature and pressure, and they determine the performance efficiency of the membrane configuration. By playing with these, you can optimize CAPEX and OPEX, so capital expenditure and operational expenditure of the plants. The effect of pressure, to increase pressure, is to eventually decrease membrane count. So an increased pressure gives an increased permeability and an increased selectivity. In other words, you reduce the number of membranes you require for the same flow. Temperature, on the other side, has a opposite effect. Increasing temperature increases permeability and decreases the selectivity. You can make the comparison to pores. So you heat it up, the pore becomes bigger, so the molecule can easier go through the fiber. So there's more gas possible to go through it, but the selectivity decreases. So for temperature, it's crucial to pick the right temperature, the right operating temperature and feed temperature of the membranes in your design phase. Next, please. Choosing the most efficient configuration. A lot of people ask me all the time, can you tell me, just give me the most efficient configuration? Well, my question back to them is always, define what's efficient for you. It's always a trade-off between operational costs as well as capital costs. Also, some configuration or considerations to take in account and factors that can influence your design are, for example, law, legislation, or you want to benefit from the local benefits like the IRA. There's intellectual property you need to take into account. You are limited to a physical footprint. All these factors play a role in making the right configuration for your RNG project. So if you ask me, give me the most optimized configuration, come talk to us and we can help you with coming to this optimized configuration. Next, please. So while membrane upgrading is the most dominant technology as well in the EU as in the USA, with almost roughly 50% of the RNG projects utilizing membranes, there are many other available techniques on the market that can also be used in biogas upgrading. I'm gonna scan roughly through them, the competing technologies, as well as how they compare to each other. So all technologies have a role in the market and they play their part. Next, please. As said, the membrane separation, the use of membranes for biogas separation has been increasing year on year, as well in the US as the EU and also Asia. Why are people choosing for membranes? While they can deliver the same performance as amines, water scrubbing, PSA, in terms of methane recovery or methane slip, or they can achieve equivalent performance, the main benefit for them is that there are no rotating parts. It's a plug and play principle. You get the black box or the membrane, you install it, and there's no rotating parts. Eventually, the performance can be increased and it's the most reliable technique possible. Next, please. Comparing all techniques one-to-one is very challenging, as choice of technique will really depend on the set performance parameters. So as said before, chemical scrubbing has its place. Only there's, for example, you need catalyst replacement by time. However, it removes H2S, so the H2S pretreatment can be different. Cryogenic separation, it's heavy equipment, high energy consumption. However, no chemicals involved. PSA, relatively low in power consumption. Removes nitrogen, can remove oxygen, which membranes can't. However, there's a lot of rotating parts, relatively high maintenance. Water and physical scrubbing. There's no chemicals, but you require heat to desorb. So for membrane, the main differentiator is that It's compact and light, or lower maintenance, and low energy consumption. There's also a con. It's the scalability. So the membrane has a certain scale, and if you increase flow, you need to have more membranes eventually. Next one, please. Lastly, I would like to show you some examples besides the well-known RNG upgrading plants we all know. And with well-known RNG upgrading plants, I'm talking about 2- and 3-stage membrane systems. However, the membranes can also be used in more unique, niche, or hybrid systems to produce, for example, biohydrogen, if that's already a term, bio-LNG, or how you can achieve a very high methane recovery to comply with emission laws, actually. Next, please. So one of the most unique projects we did is located in Japan. It's converting biogas to hydrogen, or green hydrogen. So the membrane there produces a very pure methane, and that's directly fed into the steam methane reformer. In the steam methane reformer, they use catalyst. And the catalyst is really subject to pollutants and will actually decrease rapidly in performance. So it was really key to generate a very pure methane stream there. And the hydrogen produced eventually is fuel grade and is used for transportation. So it is possible to go from raw biogas to very pure hydrogen. Next, please. Another relatively unique case we worked on in 2018 is where we supported an innovative startup that had the idea to convert biogas into bio-LNG with direct use of membranes embedded in the liquefaction process. Therefore, together with the startup, Air Products Membrane Solutions tested and designed a membrane configuration utilizing an external sweep that provides a very pure methane that is very low in CO2, so less than 50 ppm CO2, therefore directly liquefiable. Currently, they have one running plant producing 10 tons of bio-LNG a day, and they are building a second and third plant based on this principle. And this principle is very unique to our product and is very unique to production of bio-LNG. So it's possible to go from raw biogas directly into liquefaction using membranes. Next, please. Another one challenging case we worked on in 2019. In Europe and certain parts in Germany, the emission laws are very strict. And the emission laws are strict in terms of methane emissions, where generally, say, 0.5% to 1% of methane emission is allowed. Here in this particular region of Germany, only 0.1% methane emission was allowed. So meaning that our design needed to recover very high methane percentages of 99.9%. This is possible with standard 3-stage system. However, the power consumption skyrockets if you would go into a 3-stage system. This is mainly due to a very high increase in recycle. You're going to basically take more gas and feed it back to the compressor. So together with our engineers, we came up with a patented cycle, which you see below the PFD, where we basically incorporate an additional compressor or compression step between the membranes to boost the second and third membrane stage. The effect of this is eventually that the power consumption stays stable. You can see the green line that's compared with a 3-stage system in the green and the orange line, while the methane recovery increases significantly. So in this case, operational costs were roughly 50% lower versus a standard 3-stage system. Next, please. So working with membranes, and what kind of membrane can do for you? Well, a membrane in your RNG upgrading plant can give you a reliable, safe, and competitive plant. And competitive in terms of reliability and as well as energy consumption. Next, please. Triggered to learn more about membranes or even more, and if they might fit to your project, reach out to us. We have an experienced team based out of St. Louis where we also produce the membranes. So you can also benefit from the IRA benefits if you would incorporate our membranes into your RNG upgrading plant. We provide the high performance membrane separators. We support you with biogas upgrading system design, technical application support. We can provide simulation tools and design manuals. We do analysis and performance reviews. And basically, we can help support you globally. Air Products is a global organization, just as the Air Products Membrane Solutions Group. So reach out to us. Next, please. So I want to thank you for your attention. And I'm going to transfer it back to Paul and opening the platform for questions.
Okay, thanks, Rory. We've got some really great questions coming in. So walk through the pressures of a membrane system, the feed pressure, the retentate pressure, and then the permeate pressure.
So a typical pressure where the membrane is fed at is somewhere between 8 and 16 bar G, or in PSIG, 150 to 200 PSIG. The retentate basically has maybe half a bar or 10 PSIG pressure drop. So it sticks to the feed pressure. So if your natural gas grid is, for example, operating at 12 bar, that's very quite common pressure in Europe, you can directly inject into the grid. If you need to, basically inject to a 30 bar or higher pressure grid, then you need to have a booster compressor behind the membrane unit. The permeate basically can go to atmospheric pressure. So say roughly 10, 20 PSIG, or even close to 0. Depends on how you operate it and design it.
So high pressure in, high pressure out, very, very low pressure in the permeate. So all that energy is needed to cross through that membrane fiber. Got it.
Yeah.
Okay.
Pressure is the driving force for the separation here as well.
Right. So question about competitive membranes. If somebody has a system with a different membrane supplier's membrane in it, can they swap those out for Air Products, or is it all a different configuration?
Good question. One-on-one swapping out, it's something we need to look into more detail. Performance-wise, all membranes on the market, biogas membranes, perform relatively equal to each other. But still, you need to have sufficient membrane area, so sufficient membrane count per stage. However, per stage, basically, it's relatively easy to swap out, yes.
So specifically, the question came in about a 6-inch competitor's membrane. Does Air Products sell a 6-inch membrane, or is it different sizes?
Correct. No, good question. We didn't disclose sizes, but we also supply 6-inch, yes. 6-inch 5 feet are most common sold membrane in the market.
Okay. So what affects the selectivity of a membrane? Is it separating based on molecular size or polarity of the molecules? What's the main driving force on selectivity?
So selectivity is the majority is defined by the polymer choice. So these are all polymeric membranes, and the choice of polymer defines the interaction with the molecules. So basically with the CO2 and the methane. So that's one. Then we have the porosity of the fiber. So how porous is the fiber? How easily can gas pass through? And then there's a very thin separating layer on the fiber as well that also adds a little bit selectivity to it.
So the question specifically was the terms you used, fast gas versus a slow gas. Can you walk through how does a gas become fast or slow when it comes down to the membrane itself?
Good question. So first of all, it's the molecule size. So if you talk, for example, fast gases, helium, hydrogen, relatively small molecules, as well as in weight, as in how they chemically are built. And slow gases are the heavier molecules, so methane, higher hydrocarbons, so ethane, pentane, etc. This combined with the size, the porous size of the fiber, as well as the interaction of the molecule with the fiber, defines selectivity. So in this case, for example, nitrogen doesn't want to permeate or interact with the fiber, and therefore is considered a slow gas. It's the same for methane. While CO2 wants to interact to a certain degree with the fiber, and therefore permeates out of the fiber to the low pressure side.
Got it. So more questions here. What is the life of a membrane? How many years of service do you feel like is reasonable to tell the market?
So that's a good question, and also a difficult one to answer. So first of all, as you could have seen in my presentation, pre-treatment is key. If the membrane is fed with clean gas air, it can last for many, many years. The biogas or the RNG market is relatively upcoming and new. So to tell you that we have a 20-year-old reference but still good functioning membranes is will be a lie actually. But we know we do have the experience from the nitrogen market, where we have been active for almost 40 years. And that's where we see that the membranes can last up to 10, 15, and sometimes we even see a reference of 30 years plus with limited performance loss. So generally, our feeling is that it would last 10 years, roughly, if the feed is correctly.
Do the polymers in the membrane ever break down?
In what terms, Paul? They break down? How do you mean by
So
they
polymers,
cut, or?
do they decompose? Do they fracture the long molecules? Do they break apart over time?
Coming back to the pre-treatment again and the raw gas composition. So take, for example, landfill gas. We all know that landfill gas is full of pollutants, like ketones, for example. And we're still talking about polymeric membranes here, or polymeric fibers. Polymers interact with solvents. So you can imagine that if the polymer is subject to solvent exposure, that the performance will decrease, and also the mechanical properties of the fiber, so the strength of the fiber decreases. So again, pre-treatment is key here, as long as the gas is free of oil, free of water, because water basically will give condensation. There's no particles in there, then the membrane should last a relatively long time.
Okay. Question came in that says, do membranes require regeneration? I'm going to rephrase that and maybe say, do they require cleaning?
Generally, no. So there are some upset conditions where feeding clean gas again to the membrane can recover a little bit. So for example, if the membrane is just exposed to moisture and solely pure moisture with no other pollutants in it, the membrane just gets wet. Then you can basically regenerate it by drying with clean, dry air. And it will gain back performance. But there's no, like with a PSA, where you need to flush the vessels. There's not with amine scrubbing, where you need to have a desorption column. Membranes basically don't require regeneration.
Okay. What is the specification for hydrogen sulfide going onto the membrane?
So our membranes are good to up to 10,000 ppms of hydrogen sulfide. So they're very resilient against hydrogen sulfide. However, the majority, or basically all of our OEMs, do remove the H2S from the raw biogas stream due to potential issues with the oil contamination in the compressor, as well as other exposure in the system that you want to prevent. But the membrane is actually subject to a very high content without performance loss.
So how does the Air Products membrane compete with other membranes on a performance basis?
So performance basis is, as I said before, looking at our competitors, we are relatively equal, right? It can be plus minus 1 or 2 membranes in the system, but performance-wise, everybody performs equal. Our main differentiators are for sure the H2S tolerance. That's a main differentiator from our competition. And as well as that we focus on more than just a standard 2 and 3 stage upgrading cycles. We see ourselves as a technical innovation R&D driven membrane supplier. We partner with the OEMs, we develop the cycles together. The biogas to hydrogen, the biogas to bio-LNG, complying with the emission laws. Those are all examples where people come to us with relatively quite complex questions. And all of the results are things that were never done before with membranes. So I think this is where our strengths actually are.
Okay. Question came in on lead times, making the observation that we're in a time people are busy, lead times are stretching out. What is the lead time for Air Products membranes?
So the lead time is still better than the compressor. So no, the lead time is relatively normal, I would say. So generally you see that the components for an RNG plant differ between 4 and 12 months. And in that time span, we could be able to deliver as well. Depends a bit on the volume, of course, as well as the urgency.
So what does Air Products do with St. Louis versus headquarters in Allentown, Pennsylvania?
Good question. So in St. Louis, there's our actually manufacturing. That's a place where we manufacture the membrane fibers and we assemble the membranes. So we take the shell and put in the membranes, we pot them as we call that, and we make it a functioning membrane. We test it and we ship it out to the customers globally. And a part of our R&D organization is also located near the production, of course, because we need to do production test runs, etc. We have some labs there where we can do some testing. And in the Allentown headquarters, we do have the R&D, the global R&D organization of all Air Products, where all the scientists can together work on complex gas separation questions.
Thank you. So circling back on the hydrogen sulfide question, I've certainly spoken to membrane suppliers in the past, very worried about hydrogen sulfide, got to get it all out ahead of the membrane. So to repeat, you said 10,000 ppm, it's 1% hydrogen sulfide. So your membranes are tolerant of hydrogen sulfide?
That's fully correct, Paul. To confirm, our membranes are tolerant to hydrogen sulfide, yes.
Okay, okay.
And I am aware that indeed there are competitors in the market that are not able to handle any hydrogen sulfide.
So how do membranes work on a start and stop basis? Is that hard on the system if it's starting and stopping very often?
So generally, if you have a system that works cyclical, basically cycles all the time, then we need to look at the system design. Isn't it over designed, right? Preferably you have a constant gas flow because that removes the start peak from the system, where you basically are not in spec in your gas, and there's probably some improvement there to be done. However, if you would run a system cyclical, that wouldn't be an issue. Also there we can tell from experience, also from the nitrogen background, where we built, for example, nitrogen systems to fill car tires and truck tires. So you can imagine that's a really cyclical application. And we tested those cycles a couple of 10,000 times, even 100,000 times without performance loss. So also there, I don't have big concerns, but I would say that the design can be improved upfront.
Okay. Question came in about how do you remove VOCs ahead of a membrane?
So that would depend a bit on what type of VOCs. So VOCs is a very broad name, volatile organic components. The most common removal mechanisms are activated carbon. There are really good suppliers in the market who can support you with sizing of the activated carbon towers, as well as the type of activated carbon that needs to go in there. Or the other one is chilling. So basically condensing the pollutants out of the raw biogas. Primarily, you see a combination of both, because the raw biogas is wet and you need to remove the water anyways. So there's combining the two, the chilling equipment to remove moisture as well as a part of the VOCs is the major combination in combination with an activated carbon behind it to remove H2S.
Okay, very good. What is this sweet spot size range of a membrane project? Maybe on the low end and then on the high end. What scale of opportunity should people call your OEM for some type of a proposal?
So we've seen them in all size ranges, Paul. We've seen, okay, and I'm going to use the metric again, 100 nominal cubes an hour. So that's 300 scuff on the top of my head, up to 12,000 nominal cubes an hour. It really depends on the question of the end user. So for example, the 12,000 nominal cube, people would really relatively quick go to amine scrubbing or water scrubbing, for example, in those size ranges. However, in this case, the end user specifically requested membranes due to the fact that they want to have an ease of mind. They didn't want to have any maintenance or very low maintenance actually, and they didn't have excess heat, for example, for the amine scrubbing or the water scrubbing. So there were some design consideration made up front that made it possible. And generally, a sweet spot, I would say, between 500 and 2,500 nominal cubes. But that's basically the majority of the RNG upgrading plants globally.
Okay. How about temperature? What is the typical temperature that you'll find the membrane system running at? So
a typical feed temperature is normal conditions, so 20 C feed. So 20 C, don't repeat the Fahrenheit to be honest, 20 C feed into the membrane, which is just normal outside temperature. People sometimes feed warmer, but the downside is that your selectivity decreases significantly and rapidly. Sometimes you see people who do feed it colder, so they're looking at 5, 10 C, for example. Because then they have a very high selective membrane, and it gives them, for example, the very pure methane to go into liquefaction. So that really depends on what you're looking at, but generally normal conditions, normal temperature.
So how about oil? What happens if you see a little bit of oil in the biogas come onto the membranes?
Yeah, so the oil source is, in the majority of the time, is the compressor. So the raw biogas compressor is the source of the oil contamination going into the membranes. We generally recommend a safeguarding filter in terms of a small active carbon filter before the inlet of the membrane. So if there is some oil carryover from the compressor, there's sort of a last wall before going into the membrane. If it goes into the membrane, it will be almost nearly impossible to remove. You might try to sweep it or feed it with clean gas, and it might dissolve a little bit in the gas, and you might recover some performance, but basically recovering back to full performance is nearly impossible. There is a benefit, the membrane, there's also a good thing here. If you have multiple stages, generally only the first stage of the system is the one that fails, because it functions as a filter for the downstream stages actually.
So what do you see in performance if the first stage is starting to fail? Is it gas quality compromises, flow rate is compromised?
It can be multiple things. So it can be a decrease in flow. That's if you, for example, block the membrane. So you have particles you have oil, you have active carbon breakthrough, for example. That's what we've seen as well in the field. So your blade is basically blocking off the fiber. Can be an increase in pressure drop. So the CO2 is at higher pressure than normal, or the permeate is higher pressure than normal. Quality loss at the end. So the methane purity dropping.
So how does that show itself in terms of technical support? So if somebody's got a membrane system running, it's been in there for a few years, do they call your OEM for technical support, or do they call Air Products?
Also, that depends a little bit, but generally the OEM also supports the end user in maintenance terms. And generally, we partner together with the OEM. We require some data, some feedback from the OEM about plant flows, plant operating pressures, how the membranes are configured, etc. And from there on, together with the OEM, we basically do a performance analysis. So initially, we decided, or we simulated, that this would be the performance. How is the performance currently? Are we still in, say, 1-2% from the initial performance, or are we way off? And what can we do to make it, to correct it actually?
So if the stage one is struggling, do all the membranes tend to be looking the same as far as if there's contamination, or do maybe some of the membranes look differently in the first stage compared to each other?
That might be indeed the case, that they look a bit different. Of course, you always try to prevent preferred flows into the membranes, but there's always a sort of preferred flow eventually, the way of the lowest resistance. And it can indeed be that the one membrane is more fouled versus the others, or more has a bigger performance loss versus the others, yes.
So a question came in about recycle. So compared to your forward flow, what fraction are you recycling?
So the recycle depends on the methane recovery. So if I feed 100 molecules, how many molecules do you want to recover? Generally, you see that people go for 97 to 99.5% recovery. That's relatively market standard. And then you, depending a bit on how much you want to recycle and how big your compressor can be, you have a recycle, say, roughly somewhere between 30 and 60%. So it also depends a bit on the raw biogas composition eventually. If you want to go higher, you can even exceed the 100% recycle. So your recycle is more than your initial flow eventually.
Okay. So question on membrane pore size. So do you have a couple of different models of membranes that have different polymers, or is it all the similar polymer, and what is the pore size that you claim?
So the pore size is something I unfortunately can't disclose. That's a trade secret. But we do have two different types of membranes. So unfortunately, the golden membrane isn't on the market yet, where you have a very high selectivity and a very high permeability. But we do offer a high permeability, lower selectivity, and a vice versa. So a higher selectivity, lower permeability membrane. It's all relative to each other. But the benefit of doing this is that you can keep your capital, so basically the number of membranes you require in your system, in control. So you use the higher selective membrane in the first stage to do a very good initial bulk separation, while the purity, the second stage, you can use your lower selective membrane because you're already feeding relatively pure methane to that stage.
Okay. Why is two membrane stages in series better than a single larger membrane stage?
So two membrane in series is, first of all, you get a higher purity. So you can imagine it, you're putting the gas twice through the membrane, basically. You feed the gas, you do separation of methane and CO2. The non-permeate is higher in methane than you fed to it, and then you're going to feed it again through another membrane. So it increases in purity eventually. Also, what you're going to get is a recycle stream. because eventually you need to have somewhere in the mass balance to remove a stream. So in a single stage membrane, there's only in is 2 out basically. But in a series, two-stage membrane series, you have 1 in, 1 out, and 1 in and 3 out. So you can recycle something as well.
Okay. Can you comment on what the tail gas composition looks like on a typical RNG job that you're trying to get over 98% methane in the retentate?
Yeah, so a typical tail gas composition would be normally 97% plus methane, and depends a bit on how much nitrogen you had up front, but say roughly 1% nitrogen and say 2% CO2. That's the most common outlet or composition on the retentate, because that complies with the majority of the natural gas grid specs actually.
And so the tail gas would look like what on a project like that?
So
Your
tail gas
permeate.
Permeate, yeah, sorry, the tail gas permeate, yeah. The permeate would look like also similar, only where instead of 97% methane, you will find 97% CO2 actually, and the majority of the oxygen. So you get relatively pure CO2 as well, which is already sufficient to consider it as a standard industrial CO2 grade.
So what percent methane would be then in the permeate?
We design generally to less than 0.5 mole percent, because that complies with the emission laws. So the permeate is generally vented currently to the atmosphere, and the majority of the laws ask for less than 1% or less than 0.5% methane in the CO2.
So do you feel like in this world we're in of making RNG out of biogas, are you feeling like it's typically going to be a 3-stage system? Are you seeing that the most commonly, most frequently?
That's the most frequent or the most common setup. However, we see a big push towards lower methane slip or lower methane emissions. Methane is, of course, a much stronger greenhouse gas versus CO2. You see specifically in Germany, that's one of the first ones. The UK is also considering it currently to reduce it even further, and to also even make it mandatory to capture the CO2 on the biogas plant or the RNG plant. So if you have a liquefier, for example, a CO2 liquefier attached to your RNG plant, you can achieve 0 methane slip, because the off gas of the liquefier can be fed back to the main compressor, and you're basically going to recover 100% CO2 there, or methane there.
Got it. So as we start to wind down here, maybe we want to sum up, I guess, a little bit in terms of membranes are a strong, reliable upgrading technology. Given proper pre-treatment, proper maintenance, the system can give years, decades of proper, reliable service. It's low maintenance attention. Any other words of wisdom for somebody thinking about buying a membrane system?
Well, I think you summarized it quite correctly. But if I can add something, I would also say that the potential of membranes is still untapped. It's a relatively new technique for RNG production, and there are many people, I would almost say, playing around with it and doing things with it that even we look at like, really? You thought that's outside of the box. So I see a big potential in hybrid systems as well, or replacing other separation techniques. So replacing, for example, absorbent media in the near future. And then they have a big benefit at that point versus absorbent media due to the no consumables.
No consumables, but if I'm a user of a membrane system and I want to think about capital costs versus operating costs, should I maybe be escrowing some money every year for 10 years to feel like, okay, after year 10, I'm going to have to change these membranes out?
Yeah, but that's also where we can play a part in and support our OEMs. That's where we do the performance reviews for. So generally we do after like 6-7 years the first performance review to see where we stand. And this can be conducted basically every year if necessary. By viewing the system and then analyzing the system, you can see if you need to change after 10 years or maybe even 15. And then it's saving you money.
So what was the word you used for a performance review of the system?
A performance review, basically, yeah.
Yeah. Okay. So that's a service that Air Products provides.
Yes. Yeah.
And so when the OEM is building a system, are they checking gas quality out of each stage so you know how each stage is doing?
Yeah, we always recommend certain analytics on the stages, indeed, in terms of analyzers or pressure transmitters or temperature transmitters to keep in control. And if the performance, the more analytics, the better. But I also know from experience that that's the first component people save money on because it's relatively expensive to add analytics to it.
So last question for you. Footprint of a membrane system compared to other upgrading systems, how does it compare?
Footprint, sorry?
Yeah, so the size as far as the area, the installed area.
So generally what we see up to 2,000 nominal cubes can be installed in a 40-foot container. So footprint can be relatively small. Also, there's no height coming into it in a container. So that's a benefit of it. If you go into scrubbing technologies, you need height, you need towers, which basically requires a permit. It needs heavily civil works as well. While a container can be just on a concrete slab, that's already sufficient.
Okay.
So footprint, 1 to 6 containers. That's the largest one I've seen.
Yeah. So if people are interested in talking to Air Products going forward, do they call you or call the OEM?
No, they can call me, and I'm happy to connect them with an OEM if they're looking for a turnkey system. If they have interest in utilizing their membranes or using the membranes in their designs, they can also contact me, and I will support you myself or one of my colleagues in the regions, so where we are represented.
Yeah. So last question, installation, you mentioned in a shipping container, maybe some people would rather inside of a building. How about climate? How does the membrane system behave in colder climates or in warmer climates as far as just its ability to handle ambient temperature?
So the membrane, generally these containers are isolated or insulated, and they have sort of a temperature control. So it seldomly goes sub-zero. In warmer climates, it might be a bit more challenging to control the temperature in there. But then you can consider, for example, tracing on the membrane, so keep it at the same temperature. Or what we sometimes recommend is controlling the feed temperature to the membrane with a heater or even a chiller, perhaps.
Okay. Very well. Well, Rory, thank you very much. And with that, Caroline, back to you.
Thank you, Paul.
Thank you, Paul, and thank you, Rory, and your team for sponsoring today. I want to close everything out here. I'm going to remind you to please take our survey at the very end. Once you close it out, it just takes a couple of minutes to help us improve our webinars. Please look into becoming a member of the ABC if you have not already. or you can reach out to team@americanbiogascouncil.org if you have any questions about membership. And with that, I'm also going to remind you that we have 2 more webinars this month, 2 more sponsored webinars. We also have Operator School taking place this month. Look into those. And then we're going to see Rory and his team back at Business of Biogas. They are actually our title sponsors of that event in October. You can go to businessofbiogas.com for more information on that conference coming up. Thank you, everyone, for attending. The recording and slides will be sent to you later this week. And reach out if you have any questions. Have a great rest of your afternoon. Bye, everyone.
Bye.